I'm Dave Cleaver. Who am I? I'm a senior principal software engineer at Comcast. Part of that role lets me have a lot of freedom to sort of play with fun stuff that I find kind of cool. So you get to all suffer through the latest stuff that I found fun and kind of cool. So we're going to start at abstraction. I love to abstract out stuff in code. I find, people who counsel you aren't going to need it. I've always needed it. I've done it all the time, abstracted things away, found that I needed it later, and when I was asked to make a change, I was able to say, hey, yeah, it's easy. It's all abstract. It's done. Right? So we want to separate the what from the how. We want our code to be clean. We don't want to see the underlying junk that makes up how we actually get things done. We want to see exactly what we're trying to accomplish. We want to utilize simpler implementations for testing. And this is the examples you always see around, I don't want to test in future. I'd rather test in something that's synchronous. And yeah. Oh, my other nice thing that I like to say that I didn't put up here, I want to late bind everything. Everything I possibly can, I want to make that decision as far down the pipe as I possibly can. And that leaves me flexible to make that change later if I need to change that decision, if I change my mind, if I want to expand on it, whatever I want to do. I want to late bind as many decisions as I can. I do that in code. I do it in architecture. Everywhere I can put things off in terms of decisions, I will do so. So there's two techniques that I'll talk about today around this in functional programming, Tagless Final and the FreeMonad. And we're going to start with Tagless Final. So Tagless Final, to work with that, we're going to declare a trait, and we're going to abstract out the effect type. I know Rob talked yesterday about calling these things effects, so we're going to abstract out our effect. And then we're going to write our operations. What do we want to do? In this case, I based all of my example on Paul Cleary's Scala pet store. I needed a domain, and I said, oh, wait, Paul has a domain, and he already does a lot of this Tagless Final stuff that I want to work off of. So our operations are to put an order, get an order by ID, or delete an order by ID. Pretty simple. And then using this isn't that big a deal. Using it's actually pretty simple. We create an order service. We abstract out the type again. I don't want to make any decisions. I'm going to keep from doing that. And we take in our order repository algebra as an argument. And then we can write, I have to confess, I added this to Paul's code because I needed a more complex example. I write this update status method, for example. And in there, I'm going to take in the order ID, the status I'd like to change that order to. In this case, I put a restriction on my effect. It has to be a monad. And the reason it has to be a monad is because I want to do this nice for comprehension that we see here, right? And it's going to return basically an either wrapped in my effect. Essentially, that's what that either t says. So I'm going to return either an order error or an order. Now we simply call the repo to get the order, or return order not found. Or if we've got one, we're going to copy it, change the status, and then we're going to put it back into the repo. Right? What I want to say is all right here, and I'm not concerned with how I get things out of the repo, whether or not it's in future or task or Scala, cat's effect or whatever. I don't worry about any of that. Right? And ultimately, I yield out the updated order if I've completed everything successfully. So that's how I use it. Now I want to actually, at some point, I do actually have to make decisions. It's unfortunate, but So we write a production interpreter. This is straight out of Paul's code. This is the doobie order repository interpreter. We're going to extend our algebra. And we are going to put the restriction on our effect type again to say that it has to be monad, because we do some nice for comprehension stuff in there. And we're going to take a little bit of information we need for doobie. And then I skipped some stuff that was in there that isn't all that important around setting up your transactions and things like that. And you'll see I eliminated the SQL. I don't write SQL. I don't want to claim that I do. Right? So we have an implementation for our orders. Here's how we put an order, for example. And we're going to build the SQL we need. We're going to update with the unique generated keys. We're going to do everything we need to do to get this done. And I'm sure we've all written this code at some point, except me. I don't write SQL. So, right. And then the other thing we're going to build is a test interpreter, because we don't want to test in whatever effect we were running in. We don't want to test with a real database, all of that jazz. So we do the same thing again. This time, Paul was a little looser with his restrictions. We only need it to be applicative. We're not going to do 4 comprehensions, but we want to be able to do some of the stuff that applicative gives us on our effect. So we won't worry about it too much. Right? This is all going to be synchronous. And I didn't show it, but we have some setup of cache information, some random number stuff, and we write a very synchronous implementation that just sticks stuff into in-memory cache, pulls it out of the in-memory cache when we need it, and so on and so forth. It's all pretty straightforward. So what can we do with that? We have that testing implementation. We can write unit tests, we can write our property-based tests using Scalacheck if we want to. But that has some limits, right? We can test our known inputs. Those are our unit tests. We can test our possible inputs. Those are our Scalacheck tests, right? But we test these under what we consider normal conditions. Normal conditions are where I put something in the database and I get it out again. Right? Those are the kinds of things that are normal conditions. I don't know how many of you have actually worked in, say, a distributed environment. Sometimes you put things in, and what you get out is not what you put in because somebody else put it in. Or the famous last right wins, or as I started calling it the other day, other rights lose. Right? So we kind of want to be able to test that stuff too, because that's the stuff that we're actually going to find at production. That's the stuff we do find in production and have to solve. So I want to talk about generating programs. Right? We want to use Scalacheck. We'd like to derive the possible outputs of our dependencies using gen, given the inputs to those dependencies. And that's using something in Scalacheck called cogen. Now what cogen gives you is essentially turns a value into a random seed to plug into a generator to give you basically a generator that's created from the value or dependent on the value that you were given. And we'll see it's doing that. Right, so let's build a generating interpreter. Same code we had before, kind of, right? We want to extend our algebra, but we're going to put it into gen. Now there's a nice Scalacheck cats compatibility library, and that's what I use here to give me that monad instance that I kind of need later on. And we need to take in a gen that generates our options of orders, and a generator for our longs that we're going to have in there as IDs. And then we want that cogen for our long inputs. Sometimes we're given an order ID, and we need to be able to generate an order based on that. It's not really that difficult, as it turns out. We can take that order. We can generate an ID. Here we just kind of say we're putting, so we take the order's ID, we make a constant generator for it. Otherwise, we gen an ID from the long. So basically this is saying our order has an optional ID. So if we don't have an ID, let's make one. Otherwise, we'll just use the one we have. And then we're just going to copy and make sure we set the ID on that order. We're not actually putting anything anywhere. We're just going to yield out that generator. Similarly, on get, here we want to actually take our input, our long, pass it to our cogen. So we pass in our order ID, and we pass in our response generator. And that's going to generate us a generator for option orders that are based generally on whatever that order ID that we gave it is. And the same thing, delete looks pretty much the same. So it's kind of fun code to write all this Scalacheck stuff. All right, but this maybe not so useful yet, because we still don't know what we actually did. All we know is we get some random output from our code. And we don't know why we got that output. We don't know what our code did. So we need to go and trace the code a little bit. So we're going to look at creating a new trait, because you could trace in strings, but yuck. So we're going to make a new trait for our order repository tracing. We're going to make some implementations, and we're going to capture our inputs to each operation, and we're going to capture what each operation was. So we get our trace put, we take the order in, and we just extend our base trace repository, our trace implementation trait. So we have to take that now and do something with it, because this doesn't do anything. It's just data. So we're going to build a tracing interpreter. This one's fun. So we're going to implement our algebra again. This time we're going to make our type coming out of the algebra, we're going to fix it to, we're going to allow some underlying effect type that we don't care about. Ultimately, it'll be gen when we get there. And we're going to have writer t. So what we want to write is a list of these traces, right? We want to generate a list of every one of these trace objects that we are going to create. And we want to do that in whatever our effect was, and then our type will be open to whatever the type of the operation is. So I write a nice utility method, right? I want a log. Log is going to take whatever that trace operation is, and then it's going to take something in our effect, some operation in our effect that returns an A, and then we're going to wrap it up. So we'll tell the writer monad, hey, here's our message, here's what we did. We'll get that result, and we'll basically lift that other program up so that it's in the right context, and that'll be our result. We'll return that. And then we use this nice utility method to write everybody else, right? Put, we make a trace put, we wrap it up, and we send it the wrapped puts operation. So we always work off of this wrapped algebra so that we could use this theoretically and trace our production interpreter if we really wanted to. So get, pretty much the same. Trace get, take the order ID, call the wrapper, and see what happens. So why would you want to do this? Because you're crazy. Maybe you want to test code properties. So that code that I showed you at the beginning, I could write something that actually says, hey, what is the, I don't know, do I ever call delete in this code? Are there any conditions under which things I don't want to happen could happen? Are there, maybe I'm looking at, sometimes you use dependent functions and it turns out that they all went and fetched the object from the database and you didn't realize, so you called get like 3 times. You could test that. I never call get more than once. I never call delete. So here's we'll write a test. Never delete when updating the status. And my code, it was simple. We could go back and look at it and tell that it never calls delete. But if your code's much more complex, it's going to be a lot harder to tell. So we're going to build our interpreter, right? We want an order gen interpreter. So we give it our gen option. Luckily, Scalacheck is in use in the Scala Pet Store, so we already kind of have an arbitrary instance of our order that we need. Basically, we can generate orders whenever we want. Scalacheck gives us the ability to generate options of things that we can generate. We're good to go. And also, positive numbers. Pretty straightforward. We'll build our trace interpreter wrapped around that gen interpreter. So now we're generating random sets of these lists. Or we could generate random sets of the lists. We'll pass that into our order service. That's what we want to actually test. And now we have to build an arbitrary instance for these walks through our program. So we're going to have an arbitrary list of the trace objects that we're looking for. And the way that we do that, we'll call the method under test. Here I give it actual arguments, set and fixed. I could have generated the arguments as well, given it random arguments. And then what we get out of that method is ultimately going to be something, either t wrapped around my writer t with my trace stuff and my gen. So I got to do some unpacking. So I start by getting the value that unpacks my either t one level. And then I want to get the stuff that's written. So that takes my writer t and it runs it and just gives me the written stuff. It ignores the return value. And then I can write my property. I can say for all the walks in that code, assert that none of them ever call delete. And this runs, and luckily my simple code never calls delete. Although I did add a delete in there just to make sure that this would fail miserably in that case. Right, so this is the stuff that got me excited, right? Random walks through your program's testing. I think you could extend this. You could capture what the actual, you capture the inputs and the operation, but you could also capture the output of the operation. And you could do further, more complicated properties. You could make richer interpreters if you really wanted to. So you could make your interpreter do more reasonable things within the bounds of what your underlying dependency is going to do. For instance, most of the time when I put something, I'm going to get it. Sometimes I don't. I want to model that, but I don't want to model complete randomness all the time. For simplicity's sake, I modeled complete randomness. So this generates for us these. This is what walk is over a small number of runs, right? We have a trace get 5, trace get 5. We probably return none there, and our code did an error. We have trace get 5, and then we put. Now, hey, guess what? We got a random order out. This is where I said you could be reasonable, and I wasn't. We get a random order out, so our IDs look funny, but it's OK. And you see, the code was simple, so we get simple traces. So what else can we do? We talked about, briefly, FreeMonad at the beginning as an abstraction technique. So with the FreeMonad, we can encode our operations as classes. We can wrap them up in the FreeMonad, and then happiness happens, right? So let's start with our free operations. These are going to look really familiar because they're almost exactly what I had for trace. All I'm doing is I've changed the name a little bit, but I've added an output type to each one of these. Right? So put op becomes pretty much the same as trace put, but it adds that order type parameter to the end of the trait. And get op is similar, and delete op is also, they add the option order output that I had. So now I've got my free algebra. These are my operations encoded as classes. Turns out I already did that up above, but I've made a couple extensions that'll let me use the FreeMonad. So when I add the FreeMonad into this, you're probably thinking, oh man, we're going to scrap all that junk that we did back when we did the final tagless, right? Like all that's useless now. But it turns out you can reuse it. So I can make my order repository free. And I can say, I still don't want to know what my algebra is in F. This is like a good free habit. And I can extend my order repository algebra again, and I can return a FreeMonad with that algebra as its core. Right? As part of the plumbing, I'm going to take this implicit inject k. Right? This allows me later on, when I want to combine algebras together. This is the glue magic that allows me to combine a lot of algebras together. So I could have just said, I could have left off the F and just said it's always order repository op, but then I don't get a lot of options to mix things later. And I want that power. So what I'll do is for each operation, I simply, free has this nice function inject, which will inject my operator, my instantiation, my instance of the operation into that algebra. And all that's taken care of for me. All right, and I do that for each one. This is almost what we had for tracing. So now how about the generating interpreter? What's that going to look like? Turns out I'm really lazy, and I didn't want to take up your time reading a lot of the same code again. So we're going to create the order repository op as gen, and we're going to cheat. And we're going to take the interpreter I already wrote in the final tagless. And this time, we have to do things for the free monad, we're always going to see these squiggly arrows. And the squiggly arrow says, take this type with a hole in it, right? It's a function from this type with a hole in it to another type with a hole in it, essentially. That space for what the return type is gets transferred through this function. So I can take any order repository op A and generate a gen A from it. And then I have to implement the squiggly arrow, I have to implement the apply method that's going to do that operation. I want to match on any of my operations that I created. And for each one, I'm just going to delegate to that interpreter I already wrote so that I don't have to write it again, and so you don't have to see it again. But this is kind of neat, because I basically didn't make a decision. I was late binding again, right? I chose final tagless in the beginning, but at some point later on, I decided, hey, I'd like to use free. And nothing about the choice that I made at the beginning has stopped me from using free. So the other reason I like free is when I write tracing. When I write tracing with free, I can be really super generic. I can write a tracing function that will translate anything into a traced version of itself. Right? So what I want to do is take any f that can be turned into a g, and I want to trace it. And so I take in my squiggly arrow function for f to g. And what I'm going to produce is one of those functions that returns my writer t that stores up all those operations. It's going to capture them all, but it's still going to give me a g out, which is what I want ultimately. So the apply is really simple. It looks a lot like the log method that I wrote before, right? Except now the thing I'm logging is always passed in, and that also is the thing I'm logging. So I have some advantages. So I can tell in the writer context, I can say, hey, add this operation to my list, and then lift the translation up into the writer. So I run my sub-translation, and I just lift it up. And I yield out that result. And I can use this for anything. Any algebra that I write can use this. If we look back at what I wrote before for tracing, I had to implement the final tagless interface. So I had to implement the put method and the get method and the delete method. And if I come up with another interface and another algebra, I have to implement all those methods. So I have to write trace many, many times. And I don't really want to do that if I can help it. So, here I broke down all that stuff I already told you about. All right, so I can go back and I can test my code properties again. This is the exact same thing we tested before. Never delete and update. Made a couple modifications. I make this gen interpreter, which I build up it pretty much the exact same way I did before. I make my order repository free, and I pass that into my order service. And I need one other piece, which is my interpreter for free. So I need to take trace, and I need to wrap it around my order repository op as gen, using my order gen interpreter, because I was lazy. I won't stop pointing that out. And then I build my arbitrary walk again. This time it's a little bit weirder, because I have to account for that a value, but I just kind of say, I don't care what it is, right? This is a list of these things, and I don't care what's filling that type hole. And so now I call my order service update status, and I get the value out just like I did before. But now I have to do something a little different. Now when I've gotten the value out, now I have a free monad wrapped around this. So I got the either, I have now a free monad with an either inside of it kind of thing. So what I call for free is fold map. And when I call fold map, I give it that interpreter. I give it that function. Fold map will look at every single, I basically have a big data structure in my program, and it'll look at every single step in that data structure, and it'll give it to my interpreter and say, please turn this into what I need it to be. And then it'll chain all of that together for me. It does all the magic. And so now what I have out is the gen. wrapped with my writer T with my gen in it, and it's all scary. So I need to get the written value out again when I'm all done that. So now I have like my writer T wrapped around my gen with my list of operations, and I need to get the written bit out. I could also get the result if I cared. In this code, I don't really care. Right, and then this code doesn't change. My testing, whether or not I delete opt, all I did was add that little extra bit of existential parameter at the end to say, hey, I don't care what's in this walk. I'd like to know, I just want to check if the delete ops exist. So we didn't really change this very much. But some of the power that we gained is we gained the ability to combine. Free gives us the ability to combine interpreters and to combine algebras together. So now if I have multiple of these order repository algebras, maybe I have an order repository and I have a pet repository and I have a authorized users repository, I can combine all of those algebras together using some of the free mechanisms, which unfortunately I don't have a slide for, but I can combine them all together and I can trace them because the combination is still just data. It's just co-products of values, and everything is stored in basically a bunch of ethers that say like it's either from the order repository algebra or from the pet algebra or from anything else. So I get lots of like left, left, rights, but that's okay. And when I combine them together, I can still do these kind of tests. I can still test over the combined algebras. That's a little bit harder in the original Final Tagless. As you can tell, I love free, probably more than I love Final Tagless. It's a little bit harder because I'd have to come up with I'd have to combine all of those trace objects together in a similar way. I'd have to figure out all the lefts and rights and figure it out. Now I think CATS gives me some mechanism to make that easier, but I still have to do the work to do that. All right. So this all went really fast. So analyzing functional programs. So use Tagless Final or the FreeMonad. I don't think this is an either-or choice, as I kind of pointed out in this whole presentation, right? Start with Tagless Final. It's a great way to abstract out your what from your how, and to separate your implementations that have all the complex future, task, stream, whatever behavior from the code that just does business logic. And you want that separation. If you want to add the FreeMonad later because you like to test, and you think it's useful for testing or because it's just a better way to implement what you're doing, then do it, right? Add it in later. And you don't have to change a lot of code to do that. So test not just your inputs and outputs, but exercise the behavior from your dependencies, right? You don't discover that stuff until you actually stick it out in production. And you don't want to discover it when it's out in production. And check what your code tries to do. I'm sure we could do a lot more complicated stuff than I did. I did something super simple. But I can imagine, how many times do I call this method? Do I make sure I don't call it more than this number of times? Things like that. And by making these properties, I ensure that those things remain true across the lifetime of the code. When someone goes and modifies the code, I'm not suddenly going to get deletes in the updating status method, right? Nobody can add that without failing a test. I highly encourage you to take a look at what Paul's done in the Scala Pet Store. It was very useful for me. I needed a domain. He had a domain. And he's got a lot of cool stuff that introduces at least Final Tagless. He doesn't introduce free, but he does introduce Final Tagless throughout kind of the whole construction of the Scala Pet Store. And then my example code, you can find all the code in these slides at Comcast Samples, Scala Pet Store, Analyze FP. And so that does add the extra free constructions. It's got both of my versions of the test, all my interpreters, all of that information. So you can find me on Twitter and GitHub at dscleaver. And we're hiring. So check out jobs.comcast. All right. Any questions? Great. Yes.
Why is it called Final Tagless?
I wish I knew. No, I believe it's because it was named when someone said, oh, I've finally been able to make something tagless. So tagless refers to the fact that under that implementation, you're not creating classes. So you're not creating objects that have like tagged information that's stored at runtime. You can kind of avoid all of that stuff. And so I think really it's named because someone said, ooh, I'm finally tagless. Done, that's what I'm going to call it, right? Names are hard. Yeah. Yeah, so cats used to call it natural transformation. Now they call it function K. So it is the same thing. Yeah. I never asked.
It's the same thing minus a law.
Right. Oh, it's minus a law? Oh, interesting. So also, you know, really it is just function at like a higher kinded level. So that was probably part of the reason to rename it as well. So, and it, you know, I'm sure there was lots of jargon and other fun stuff that you may not understand in here. Like, feel free to reach out to me on Twitter, here at the conference. I'll be here hopefully for most of the rest of the day. Feel free to come up and ask. Like, I love to teach this stuff, right? I teach this stuff at work. I love to teach it. I love to explain it to people. There's no dumb questions. There's just asking the same question multiple times. And that's not even necessarily bad, so. All right, any other questions? Yes?
I would like to ask a question. So, what about the efficiency of the splitter code? Because I saw, eventually you end up with big case pattern matching, right?
Right.
So, imagine you are running like live production code, and how does it impact the efficiency?
If I'm running free, how is it going to impact the efficiency of my live code? I haven't done the tests. I think a lot of times we fight for efficiency in places we don't need to. That was I gave a nice love letter to free last year, and that was my opinion then too, right? Like a lot of times we worry about efficiency where we may not need to. If it's not efficient, don't do it. Like take it out, change it to something else. But at least you have this tagless abstraction to kind of like still make your code clean, but like hide the efficient stuff under the hood. I hope that I kind of punted a little bit, but. And there's Freestyle. I don't know if you've seen it. They do a lot of stuff to try to make some of that pattern matching stuff go away and be faster under the hood. And they support this kind of tagless final style and free monads if you want it. And they kind of handle all the combination, and they try to do things much more efficiently if that's a concern. So. Cool. Great.